Right, we're going to move on to this question. And you've got the electronic configurations there. So that's just one. That is 2.1 because you've got 2 electrons on the first shell and 1 on the next one. So this will be 2.4. This will be 2.245.6. So on the outside, you've got 1, 2, 3, 4, 5, 6. Be 2.6. Same with the next one, 2.8. And then you've got 3 here. You've got 1, 2, 3. So it'll be 2.8 dot. And then you have, look, 1, 2, 3, 4, 5. So it'll be 2.8.5. If you look, this has got a full outer shell. Right. That's going to be hydrogen because it's only got 1 electron. This will be lithium. And then if you go across your periodic table, you see these. So this here has got 8 electrons on the out, so it'll be in group, right, they label it group 0. Sometimes people call it group 8. Right, so this is group, well, this normally floats about on its own, but it's still group 1. So this is group 1. Let's change color. G1. This has got 1, 2, 3, 4 on the outside shell, so it's group 4. This will be group 6. That's group 8 or group 0. That's called a noble gas. Right, noble gas. And then you've got this, it's got 5 on the outer shell, so it will be group 5. So now, from here, we need to answer these. Right, I need a periodic table. Right, okay. A noble gas. Remember we said noble gases have full outer shells. So noble gas will be E, we already know that. Something that contains 3 protons, because we said the number of protons equals the number of neutrons in any atom. Right, a number of protons is 3, so number of electrons will be 3, so that is B. Them two are done. Phosphorus. Right, let's look at phosphorus. Let's look up on the periodic table. Right, we've got periodic table here. Phosphorus is, I know it's P, so it's this one here. Right, so it's going to be 31, 15. So let's go back. Okay, P 31, 15. So this represents the number, it's called the atomic, I'm gonna keep repeating it. It's called the atomic number, it stands for the number of, and in any atom, the number of protons equals the number of electrons. Right, so you've got 2, 10, 15. That matches with that. So it will be F. What's the top number called, by the way? This number here is called RAM, relative atomic mass. There you go. It stands for the number of protons plus the number of neutrons, both of them. Right, an element in group 4, so it's got 4 electrons on the outer shell. It's that one. So it's C. An element in period 3. Right, okay, period 3. Let's have a look at the periodic table again. Right, that's the period. That row is a period. That row is a period. Right. Each period tells you the number. Right, so the period it is in equals the number of electron shells. That's it. That's what we've got to know. So let's go back. So which one has got 3 electron shells? And the only one that's got 3 is here. 1, 2, and 3. So it's F. And then finally, an atom with a full outer shell of electrons. So we said you're allowed 8, and it's a noble gas. They have full outer electron shell, so it will be E. Right, okay. Let's look at this. Atoms A and D combine to form a compound containing covalent bonds. What are covalent bonds? Covalent bonds are when atoms share electrons. Right, and the watch this, the electrostatic forces of attraction between the shared pairs of electrons and both nuclei. A covalent bond is an electrostatic attraction between a pair of electrons and the nuclei of 2 atoms. There you go. So yes, with reference to the electronic configurations, the most likely formula for A and D. Right, let's go to A and D. Right, A is going to form a +1 ion. I'm just going to call it hydrogen. And it's going to form 6, 2, 4, 6, 8. So oxygen is going to form a 2- ion, or -2 ion. Let's write it that way. But let me take it down then. So watch this. You've got hydrogen and you've got oxygen. That's going to form a -2, and this is going to form a +1 ion. Now, if you look carefully, that 1 and 2 are not the same. I'm not interested in the signs. Because they're not the same, we cross them over. So we end up with H2O1. But we don't need to write 1. We just write H2O. So it'll be water. Right, let's keep going. Should we do this? Is this worth doing here? Okay, let's just run with it. Right, what you want to do with this sort of question, when they want you to work out the empirical formula, what did we say? There's 4 types of formula in there. There's the displayed, there is the structure REL formula. Then there is the molecular. You have empirical formula. So you've got all these. Right. 1, 2, 3, 4. We're interested in the empirical. This just means, let me give you an example. If I said to you C3H6, I can write this in its simplest form. I can cancel them down, divide it by 3, divide that by 3. So my empirical formula will be CH2. Right. The titanium ore contains a composition by mass. Right. That the empirical formula is that. So what we do is write down the elements and oxygen. Just get into this habit if you can. Right. So those are the elements that they've given here. I'm just copying them. And what you can do is you can say the mass that they've given you. We'll pretend that, look, this is 36.8 grams. 36.8 grams. This is 31.6 and this is 31.6. Right. We've worked out the mass. Right. Then we work out the relative atomic mass, or 56 for iron, 48 for titanium, and 16. You can get this from the periodic table. From the periodic table. Let's go look at it actually. Right. So iron is here. That's the number we're interested in. 56. Titanium is 48 is down here. No, 48. Come on. Where's TI? Can you see TI anywhere? I cannot see TI. It is no good. There you go. Titanium. We're after 48, and oxygen is always up here. The good old faithful oxygen is 16. So we're after that number, and that number, and that number. We're going to take those across. Well, we have taken those across. Right. Now all you simply do is mass over AR. Divide these two numbers. When you divide these two numbers, you get the number of moles. So I want you to learn this structure. Put the mass there, put the relative atomic mass there, and then you work out the number of moles is simply these two numbers divided by each other, and you're going to end up with 0.66, 0.66, 1.98. Okay, and then we want to write these in the simplest form, so we divide, listen carefully, you divide by the smallest number. So I'm going to divide them all. I'm going to divide this by 0.66. I'm going to divide this by 0.66. I'm going to divide this by 0.66. So the ratio will be 1:3. So that's where you get 1:3. Okay, so just look, listen carefully, learn this structure. If you want to get good marks, learn this structure. Right, let's keep going. Right, there's the equation: titanium oxide, chlorine, carbon, titanium chloride, carbon dioxide. Which of these elements has been oxidized? Right, oxidation is it's a 2 marker. Oxidation is so we know oxidation is the gain of oxygen, or remember the oil rig. Oxidation is loss of electrons. Oxidation, let's write that. Oxidation is loss of electrons. Reduction is gain of electrons. 1, 2, 3. Okay. Right, so it's any one of these, but in this case, can you see titanium has lost oxygen and carbon has gained oxygen because it's become carbon dioxide. So we can say carbon has been oxidized. Why? Because why? Because carbon has gained an oxygen, or gained, forget that, and gained oxygen. Done. Let's move on. Right, I want to do all that, and we need to write a chemical equation for the reaction between titanium chloride and magnesium. So they've given us titanium chloride, which TiCl4. They've given us that up there. We need to add magnesium to it, and then we're going to end up with titanium and magnesium chloride. Now, we've done magnesium chloride before. I know magnesium is a 2+, it's in group 2. Cl is -1. Let's just put -1 there. Right, these two numbers, I'm not interested in the signs. These two numbers are not the same, so we're going to cross them over. So we end up with Mg1Cl2. But what did we say about this one? We don't need to write it. So our one is MgCl2. So I can write MgCl2. Now I need to go back and start balancing. I've got 4 chlorines. I've only got 2 here, so I'm going to stick a 2 there. I've got 1 titanium, 1 titanium. I've got 1 magnesium, and I've got 2 magnesiums here. Right, so I need to put a 2 there. Right, the question you might be asking is, how have we got 4 chlorines? We've got 2 here, and we've got 2 lots of that. What they're trying to say to you is, look, you've got Cl. Let's get rid of you. Get rid of you. You've got chlorine runs around in pairs. What is it called? It's a diatomic molecule. What is it? Diatomic molecule. Right? But that's only got 2, so we need 2 lots of those to give us 4. So look, you've got Cl2 and Cl2. 2 there, 2 there, you end up with. Right, suggest why this reaction cannot be successfully carried out in the atmosphere of air, because it will react with oxygen. You can say titanium might react, or magnesium might react with oxygen. Suggest why the mixture is crushed. Right, normally that's to do with speeding up the reaction surface area. So if you add it to water, you want it to dissolve. So it dissolves more quickly. Right, okay. Let's see. Mixture is crushed. What are you crushing? Titanium chloride. Okay, so let's not use the word it. You've seen the mark scheme, they don't like the word it because it's not obvious. So the magnesium chloride dissolves more quickly. Describe the bonding in metal. Doesn't matter whether it's titanium, aluminium, or anything. What's the bonding in metal? Whoa. So there's our metal. Remember we said it consists of layers of positive ions and a sea of delocalized electrons. So it's a layer of positive ions and a sea of, so they're asking about bonding, sea of delocalized electrons. I can't spell electrons anymore. That is no good. Change color. Electrons which attract each other. What was the ideal answer for that? Can you remember? It is the static forces of attraction between what? Positive ions and negative delocalized electrons. Right, let's keep going. Oh, what is covalent bonding? So this will always start like this: that electrostatic forces of attraction between what though? Between shared pairs. No, I can't spell pairs. Pairs of electrons and both nuclei. Use the word both. Although nuclei is plural, it just makes it clearer. Draw a dot and cross diagram for ethane. Only show outer electrons. Ethene. So ethene is a hydrocarbon. A hydrocarbon contains only hydrogen and carbon atoms. There's two groups. One is called an alkane. One is called an alkene. Alkane has got one E, it's a single bond. So single carbon to carbon bond. That's an alkane. Alkene has got two E's, so it's got a double bond. Each carbon atom has how many bonds? 4. So look, 1, 2, 3, 4. The other carbon has got 1, 2, 3, 4 because it's sharing those. So we're after this because you've got 2 carbons and 4 hydrogens. What's stuck at the end of them bonds? Hydrogen. So what we've got is, so we want, okay, you've got carbon, you've got hydrogen, you've got hydrogen, hydrogen, and hydrogen. So hydrogen's got one electron to share, and then we've got carbon gives up that, shares that, shares that, shares that, shares that, shares that. Now this carbon will share 1, 2 electrons, and this carbon will share, let's use another color, these 2 electrons. No. 2, 4, 6. No, I am lying. What is wrong with me? Do you know what I've just drawn? Silly person. What have I just drawn? An alkane. They don't want ethane. They do not want ethane. They want ethene. That's what happens when you fall asleep. So there's going to be, let me get rid of, so I don't need this hydrogen. I don't need this hydrogen. Right, so we've got, let me get this right. What color was that? Red. Okay, what I'm going to do is change that to green, change that to green. So I know carbon's got 1, 2, 3, 4 on the outer shell. This carbon's got 1, 2, 3, 4 on the outer shell, and all together you've got 1, 2, 3, 4, 5, 6, 7, 8. I think it's better if I put this here next to it. So that would be it without all the highlights. Can we get rid of them, do you think? Can we get rid of that? Get rid of that. That's easy to get rid of. Is it easy to get rid of that? Yes. Easy to get rid of that? Yes. Can I get rid of that? Right. It doesn't matter. There you go. That's what the dot and cross diagram is for ethene. Lesson for lazy people like me. Read the question. That's a message for me. It's not for you, sensible students. Right, okay, you've got substance A, both covalently bonded and have simple molecular structures. There's the boiling points. That's got a higher boiling point. That's low. Right, when I use the word high, I mean relative compared to that. Right, so think about that for a second. Minus 42 is smaller, lower than minus 0.5. We need to explain. Right. Simple molecular structure is, you've got a molecule. There's H2O. There's H2O. There's H2O. There's loads of them. What's holding them together? Weak intermolecular forces of attraction. What am I doing? Why am I doing that for? I don't know. So that goes to 2, that goes to 2. There you go. Right, these are weak intermolecular forces of attraction that require little thermal energy to break. What is it down here? What am I going to say? Yes, okay. Why is it simple? Why is it a simple? Why is it a simple molecule? Because you can count the number of atoms in each molecule. Right, so we can say, why do they have low boiling points? It's because they have weak intermolecular forces of attraction between the molecules, which, let me change color just to let you know. So that's the first part. The second part is which need little thermal energy to break. There you go. Right. Suggest why boiling point of B is higher than boiling point of A. Right, okay. So one marker. It just means that the intermolecular. No, the word inter means between. Oh my word, that was very clever, wasn't it? It's like invisible. It's a bit like some of these students' papers. You never see them. Never see any writing on them. I think they're using this technique, aren't they? That's quite good. Look, my paper. So what they do is they get that and it disappears. Oh, what about this one? My paper. They get that and they do that and it disappears. Fantastic. That's what. There's one of my students called. I think he does that. That's a good technique. That I'm gonna send him this. I'm gonna say, look, this is the technique you use. That's why I can't see any writing on the page. Anyway, I digress. The intermolecular forces are weaker, so it requires even less energy than. Right, empirical formula again. Right, substance B. Determine. B has an empirical formula of. And. Right, okay, so what they're saying is C2H5. If I add up 2 carbons, 1 carbon weighs 12. There's 2 carbons, so I'm going to do 2 times 12, which is 24. I've got 1 hydrogen weighs 1, and I've got 5 of them. I've got 5. So my total mass is 29 because I've added these 2. Let me do that again. So 2 carbons, each carbon weighs 12. I've got 2 of those, and then each hydrogen weighs 1, and I've got 5 of them. So I've got 24 plus 5 equals 29. Right, the total mass, the molecular mass, relative molecular mass is 58. So I do 58 divided by 29. I want to know how many 29s there are. And the answer is 2. Oh. So all I do now is take that number and multiply each one of these by that 2. So I end up, instead of C2H5, I double that, it becomes C4, and I double that, it becomes H10. There you go. Jobs are good in. Where are we? Right, okay, let's have a look. Right, what we'll do is we'll finish this off and call it quits on this video. Substance X is also covalently bonded, but its structure is different. Has a boiling point of 2230 degrees Celsius. Explain in terms of its structure. Right. If it's got a high boiling point, you've got to say it has a giant covalent, in this case covalent, because they've said it's covalent structure, which has, you can do it this way, has many strong covalent bonds that require lots of thermal, I like to use the word thermal energy to break. or overcome. There you go. Right, we will call it quits there.